Welcome. Today I'll be teaching the power of matrices in engineering. I am Rami Tawfiq. We're gonna start off by the introduction, of course. Imagine trying to simulate a bridge collapsing, a rocket launch, or heat flowing through metal. All of this starts with matrices. Every time engineers try to predict how complex systems behave, they turn to matrices. Definition of matrices. A matrix is a rectangular array of numbers arranged in rows and columns, denotated typically as A equals to Aij, where Aij represents the element in the ith row and jth column. Matrices helps us organize data, represent systems of equations, and perform calculations that scale across multiple dimensions. Here's an example of a matrices. This is a 3 on 3 matrices, as you can see, 3, 4, 0, 1, 5, 9. Key concepts. Matrix notations. Matrices are denoted by uppercase letters such as A and B. The size of a matrix is given as M and N, where M is number of rows and N is number of columns. Basic operations. Addition only possible between matrices of the same size. Scalar multiplication. Each element is multiplied by a constant. Matrix multiplication. Core operation in engineering. The number of columns in the first matrix must match the number of rows in the second. Example. Multiplying 3 times 2 matrix by a 2 times 1 matrix results in a 3 times 1 matrix, often used in transforming vectors in 3D simulations. Determinant and inverse. The determinant of a matrix tells us whether it's invertible. The inverse of a matrix, if it exists, allows us to solve systems like ax equals b by computing x equals to a to the power of -1 times b. In engineering, this is crucial for solving systems of linear equations that model real-world systems. Applications of matrices in engineering. Structural engineering. Structures like bridges are analyzed by modeling forces in beams and joints using a system of linear equations. These systems are encoded in matrices and solve for equilibrium conditions. Electrical engineering. Circuits follow Kirchhoff's law, which form equations for current, voltage, and loops. These equations are translated into matrices and solved using linear algebra techniques. Example. Nodal analysis of an electrical grid results in A times X equals B system, where A represents resistance and X represents voltage. Mechanical engineering, which is my module. Finite analysis, FEA, involves breaking down a complex object like a car or plane wing into small manageable elements. Each element's behavior is described using matrices, and the full simulation is a massive matrix system, representing the physical responses to forces. Real-life examples. Simulating a car crash. A modern car crash is modeled as a collection of thousands of finite elements. Each part, frame, bumper, doors, is represented by a matrix equation. During crash simulations, each engineer used these matrices to analyze stress, deformation, and energy distribution. These allow engineers to optimize materials and structural design before building physical prototypes, saving millions in R&D. Here's a matrices question. How do we solve it? Let's solve by thinking. Solve this following system of linear equations using matrix inverse method. The question is 2x plus 3y equals 8 and 5x plus y equals 7. Step 1. Write in matrix form. We can write this system as ax equals b, where a is 2, 5, 3, 1, x is x over y, and b is 8 over 7. Step 2. Find the inverse of a. To find the inverse of a 2 times 2 matrices, we find 8 to the power of -1, which equals to 1 over denotated a times d minus b minus ca, where a is a matrices of A, B, C, D. So far, A equals to 2, 3, 5, and 1. Denotate A is 2 times 1 minus 5 times 3 equals to 2 minus 15 equals to negative 13. Now, we know that a to the power of negative 1 equals to 1 over negative 13 times 1 times the matrices 1, negative 3, negative 5, 2, which brings us to the bigger matrix 1 over 13, 3 over negative 13, 5 over 13, and 2 over 13. So 3 multiply a to the power of negative 1 times b, x equals to a to the power of negative 1 times b, which will give us x equals to 1 and y equals to 2. Conclusion. So next time you see a skyscraper, drive a car, or marvel at a rocket launch, remember it's not just steel wires making it possible, it's the matrices behind the scenes doing the math no human could do alone. Matrices aren't just numbers in the box, they're language in physical reality, guiding how we build and shape the modern world.